Welcome back to the mini course on integrable and non-integrable quantum spin chains. So this is part 2, where I discuss the proof of the absence of non-trivial local conserved quantities in the model with magnetic field. By trivial local conserved quantities, I mean quantities like the Hamiltonian itself, or in some case, like the total magnetization, which can easily be checked to be conserving. In this case, the Hamiltonian is the only trivial local conserved quantities. Okay, so let me fix some notations and tell you the main result. Okay, so let me recall that we are working on this one-dimensional chain with L sides and considering spin 1/2 quantum spin system on this lambda. So this is our Hamiltonian. We have nearest neighbor interaction XX and YY, and also the magnetic field in the X direction. We impose periodic boundary condition. By products of Pauli operators, we simply mean products of Pauli operators. They are written like this, and they are simply the product of X, Y, Z. Okay, and they live on this support. Okay, so these are examples. So we'll simply X2 is an example, or this B, X2, Y5, Z6 is another example. Okay, by P, I denote a set of all products, and I include the identity operator. In this case, the support is vanishing, support is empty. And it is clear that P is a basis of the whole space of operators on this chain lambda. That means any operator on this spin system can be uniquely expanded as a linear combination of products. Okay, I think that this is clear. And in this method of Shiraishi, it is essential to characterize the sides of each product. And in this one-dimensional case, this is rather trivial, and we should only look at the length of products. And now this is a simple example. In this case, the length is 1. In this case, this consists of 3 Pauli operators, but we don't say that the length is 3. We should look at this connected region, which is covered by the support. And in this case, the length of this region is 1, 2, 3, 4, 5. So we say that the length is 5. Okay, so more abstract definition of this. So the length is a minimum L such that support of A satisfies this for some A. But anyway, I think this example will tell you what it is. Okay, by a candidate of a local conserved quantity with maximum length K, I mean this kind of operator. This is simply the linear combination, simply a linear combination of products with arbitrary complex coefficient. And without this, you can express anything, as I said. But here we are restricting the length of products to be less than or equal to some number K. Okay, and so this K is the maximum length. So for this to be meaningful, we assume that Q is non-zero for at least one A with length K. Okay, so this is maximum length. And we say that Q is a local conserved quantity if and only if it commutes with Q. Okay, and I say C 1b, part 1b, page 9. So let's go to part 1b. This is part 1b, page 9. And here I discussed how to construct local conserved quantities for the solvable XY model. So this is different from our model. But in this case, we have seen that this is a local conserved quantity. And it's non-trivial because it is different than the Hamiltonian. And in this case, this consists of sum of x, z, x, y, z, y. So in this case, we have k equals 3. Okay, the length 3. Maximum length is 3. And here you have sum of 2L products. Okay, so this is an example. Okay, going back to part 2. So the main theorem is that we don't have something like Q3 here. If H is non-zero, then Yamaguchi, Chiba, Shiraishi proved that there are no local conserved quantities with maximum length K, where K is in this range. Okay, and well, this upper bound is L over 2. So when L is large, this L over 2 is a huge quantity. So actually, this is not really local. It can be really extended. And also, this upper bound is meaningful because if you look at the quantity h squared, this is clearly a conserved quantity, of course, commutes with h. And if you expand this, then you find that the length, the maximum length, is slightly larger than L over 2. So this upper bound is actually optimal. Okay. And so I will discuss this at the end, but this strongly suggests that the model with non-zero h is non-integrable. And as I said, H is a local conserved quantity with maximum length 2. Okay. And if you try hard enough, then you can also prove that the only local conserved quantity with K in this range is a constant multiple of Hamiltonian. So this is a very strong result. But I won't go into this proof. It's a kind of tedious. Okay, so we're going to prove this theorem following the original proof by Yamaguchi, Chiba, Shiraishi. And I will stress that the proof is not short, but it is nothing really difficult. It's really elementary. You never use fancy mathematics or fancy technique. You just need clever ideas. And all these clever ideas goes back to Naoto Shiraishi's 2019 paper, which dealt with something called the spin 1/2 XYZH model. And this is something different. And I would say that the proof of the absence of non-trivial local conserved quantities for this model, XYZH model, is much harder than what we are going to discuss. Okay. I will discuss. So now I'm going into the proof. I will describe the proof, and I will start from something that I call basic relations. Okay. So since we are dealing with the absence or presence of conserved quantities, we shall look at commutation relations with Hamiltonian. So to begin with, let's look at a product that's simple, and also take another product H, which is a piece of Hamiltonian like this. So our Hamiltonian is simple, and it consists of 3 kinds of pieces like this. And you consider commutator of this product and a piece of Hamiltonian. And of course, if these 2 guys are far away, then they commute with each other and you get 0. And whenever it is non-zero, then you find that it is some non-zero constant times a product. Okay, you don't get nothing much more complicated. And in this case, we say that A generates B with H, or B is generated by A, because by taking commutator of H and A, you get B. Okay, so let's look at some examples. Okay, so it should not be too complicated, but should not be too simple. So let's look at this. So this is product of 4 Pauli operators, and it has length 4. Okay, and there are different kinds of pieces of Hamiltonian. So there are several different patterns, but I will say that and there are 3 patterns. But I would say that this first pattern is most important for us. So I will discuss this carefully. Okay. So now, okay. So the only thing you want to use here is this. So this is part 0, introduction. I'm sure that you're familiar with this, but what we are going to use is this basic commutation relations for Pauli operators. Okay, so again, go back to part 2. So now let us first consider commutation relation with y1, y2. So here you have y1, y2, but it's clear that you can forget about these things when taking commutator. So you just compute a commutator y between y2 and x2. Then you find that this is minus 2i z2. Okay, so that's why you get this. You have minus 2i here, and this x2 is replaced by z2. Okay, and similarly, if you take a commutator with x5, x6, then you get this. Okay, now here, this is so important. And I will stress that in this case, the support of B, okay, these are B. This is B, or this is B. The support of B is strictly larger than the support of A. And also in these cases, the length of B is larger than, so this has length 5, this has also length 5. So the length of B is larger than that of A. Okay, and since this is important, let me look at this more carefully. In this case, so this is B, and so B is obtained by taking the commutator between YY and A. And so this became larger, longer. And we have sort of appended this y1 to the left end of A. And after this appending, look, here you have z2. But this is rather important. We did this with y and x, so we got z. And if we had, like, say, z, then we can take commutator and you get yx. But that's the only thing you can have. You can never have like y and identity operator because nothing gives you this, or you cannot have y because you have to take commutation relation. This is important. So this is same. Here you have x and here you have z. Okay. All right. So there are cases where the support does not change, and this happens if you take the commutator with this x that comes from the magnetic field term, and if you take commutator with x3, commutator of x3 and a, and then this becomes z3, or in this case, this becomes y. Okay, and in this case, the support doesn't change. And this is not important for us, but sometimes support becomes smaller. And this happens, for example, if you take the commutator with y3, y4, y3, y4, and then the relevant commutator is this. But in this case, you have y3 in common, so this you can pull this out, and you have y3 squared. This is simply 1, and you only have to look at this commutator. So you get this. Okay. So in this case, the length is still 4, but the number of Pauli operators decreased. And in this case, the number of Pauli operators decreased, and also the length became shorter. Okay. But actually, we do not have to look at this very carefully. And these are only 3 patterns and nothing else. For example, to see this, for example, look at this kind of commutator. Probably you will first think that you get something new by taking commutator with this. But in this case, look, so we have to consider the commutator of this guy and this guy. And since Pauli operators on different sites commute, you can just rewrite this in form, and then recall that this is again part 0. Recall that these Pauli operators anti-commute with each other. So we use this. By using this anti-commutation relation, you get this, and you got 2 minuses. So you have this. And this shows you can rearrange this, and okay, you rearrange this. You can rearrange this to get this, and this shows that these 2 guys commute. So you don't get anything from this. So these are the only 3 patterns. Okay. Now, what we want to consider is commutation. This is the commutation relation between the Hamiltonian and a product A. But now we almost know this because this H is simply the sum of these pieces of Hamiltonians. So what you want to do is simply sum up this commutation relation. And this is sometimes you get B with this, but most of them are 0. So what you get is this. Okay. And so this is expanded in terms of B, and here this coefficient is non-zero when A generates B. Okay. So this is an example. So I always make mistake, but if you take the commutator of this and this, and then I think this is, you get this from y1, y2, and so on. You get this from magnetic field, and anyway, I hope this is okay. So it's something like that. So it's nothing really complicated, and this coefficient lambda AB is either like plus minus 2i or plus minus 2ih. Okay, that's simple, and you can always compute. Now, recall that our candidate of a local conserved quantity is this, and we are interested in this commutation relation. So you simply plug this in and use the linearity of commutator to commutation relation to get this, and then you substitute this into here. Okay, now since both the summations are finite sums, you can exchange the order. So you first sum over B, and this is the coefficient. Now we find this. Now the condition that Q is a conserved quantity is this, and this is equivalent to the statement that this is 0. But since, as I said, since B is all B's are independent, that this guy is 0 means that this coefficient is 0 for any B. So we get this thing. This condition that the commutator is 0 is equivalent to the statement that this is 0 for all B. Okay. And recall that this lambda AB, this is simply 2 plus minus 2i or plus minus 2i. This is something already very well known and easy to compute. And this QA are coefficients of, these are unknown coefficients for this candidate of conserved quantities. Okay, so you can regard this as a couple linear equation for determining this unknown QA. Okay? And we shall call this relation star, the basic relation, and use this repeatedly in this lecture. Okay, now let me just first mention a very simple application of this basic relation. Suppose that there are products A and B such that A is the only product with length less than or equal to k that generates B. A is the only product that generates B. Then QA must be 0. Why? Well, this is very simple. If you look at the basic relation for B, then since A is the only guy with non-zero lambda, so this basic relation becomes simply this. And lambda is of course non-zero, so you just get QA equals 0. Very simple. This is so simple, but we are going to use this repeatedly in the proof. Okay, now let me discuss the basic strategy of the proof, which was of course developed by Naoto Shiraishi in his 2019 paper. And first of all, we fix the maximum length k in this region. Okay? We then assume that there exists a local conserved quantity with maximum length k. This means that this guy is a conserved quantity and QA, the coefficient, is non-zero, at least for one A with length k. Okay. Now we can use the basic relations for all B, but of course there are so many B and so many basic relations. So we use selected sets of basic relations in a clever manner. And Naoto has developed a strategy to do this in 2 steps. In step number 1, we use the procedure that we call Shiraishi shift. Of course, Naoto doesn't call it that way, but I call it Shiraishi shift. So that we use the procedure that we call Shiraishi shift, and I hope you call it too, to show that this coefficient QA is 0 for any A with maximum length, unless A is of some simple standard form. Okay. And in this case, standard form is really simple, x, z, 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 z. I will tell you this. And of course, actually, the standard form depends on the model that you're considering. But anyway, you do this in the first step. And you know, this makes the problem much simpler because the products with length, there are so many different products with length k. But this shows that you have to deal with only limited number of them. And then in so this step 1 is rather general. And then step 2 becomes much more puzzle solving and much more model dependent. And then you try to find a very nice selected sets of basic relations to show that even for this standard form, QA equals 0 for any A with length k. Okay. And by putting these together, we find that QA is the coefficient QA is 0 for any A with length k. But of course, this is in contradiction with this condition. So this contradiction means that there exists no local conserved quantity with the maximum length k. Okay, so we shall now follow this strategy. So in what follows, we fix k. And we assume that there exists a local conserved quantity with maximum length k. Then we can make use of these basic relations. Okay, so let's start. So I will start, of course, with step 1, and I will discuss the Shiraishi shift. Okay, now I take any product P with length k. And I recall that this is the maximum length within our candidate of a local conserved quantity. And now suppose that support of A is written like this. So this is the leftmost site, and this is the rightmost site. Okay, and in this case, they must satisfy this. And since k is, we use this only here. Since k is less than or equal to L over 2, you can uniquely determine this leftmost and the rightmost sites. Okay, the first lemma says that QA is 0 unless both the following conditions are satisfied. What are these conditions? It looks a bit complicated, but it's simple. And actually, this is something you have already seen. Okay. The first condition is about the left end of A, and it said that the leftmost site should contain X or Y. In this case, it contains X. And also, it says that this next one, the next site, the right neighbor, should not be an identity operator, and it should not be the same as this one. Okay, so in this case, this cannot be an identity, or this cannot be X. Or this can be either Z or Y. And the condition number 2 is the same thing for the rightmost site. The rightmost site must be X or Y, and this one, the next one to the left, cannot be an identity or cannot be the same as this one. Okay, so this is not yet the standard form, but this restricts the form of A that we should consider. Okay, here's the proof. We define B like this. What is this? Well, we are taking commutator with something on the support u bar and u bar plus 1. Okay, so we in this case, if the A is this, then the rightmost side contains X. So in this case, we take commutator with y. And then here I have this to make this a product. And then the result of this taking commutator with y is, of course, as we did this. So by doing this, we get B, the product, with length k plus 1. And by definition, A generates B. The same for the other cases. So we have this relation. Okay, now we ask, is there any product A prime other than A, which with length less than or equal to k that generates B. Okay. And if the answer is no, if there's no such A prime, then A is the only product with length less than or equal to k that generates B. In this case, we can use this simple lemma A to conclude that QA equals 0. Okay. So in order for QA to be non-zero, the answer must be yes. Okay. Suppose that the answer is yes, and this is an important point. We are only looking at a product which has length k or less than k, and now B has length k plus 1. Okay. So when considering A prime, the only thing you can do is to sort of add some new Pauli operators by taking commutation relation to get B. So the only thing you can do is to add a new site on the left or right. But adding to the right is already done. This is A. And so the only thing you can consider is the A prime which lives on this support, which looks like this, and to get B by appending something to the left, like this, taking commutator with XX or YY. In this case, if you take commutator with XX, then you recover this B, and that is the only thing you can do, right? And so, okay, so if the answer is yes, the only possibility is that support of A is this, and of course the length is k, and it generates B like this. And then you find, like from the consideration that I explained already, the left end of B satisfies this, okay? Because this must be either X or Y, because you should take commutation relation. And also this guy should not be identity or should not be the same as this thing. So we have shown this property for B. But look, the left ends of A and B are the same. So this means that 2 is satisfied for A. So this we have shown this, but to show this 2, the condition 2 is necessary. You can simply switch the role of left and right and repeat the same thing. Okay. So this proves this important lemma 2. Okay. And now, actually, we have already seen the Shiraishi shift. This is shifted to this. This is actually Shiraishi shift. So let me discuss this in more general. Okay, so again, I take a product B with length k and assume that it satisfies conditions 1 and 2 of this lemma. Okay, so this is an example. It satisfies both the conditions. And then I do the same thing. I first of all consider a new product B with length k plus 1 by taking commutation relations like this. And now there are only two cases. This is the same thing as before, but now there are only two cases. And if it is the right end is x, you take commutation relation like this. The right end is y like this, you take commutator with xx to get this. So you get this longer one, and then you ask what is the unique other product that generates B, A prime. And well, you find it. And you can generate B by a unique A prime either by this or by this. Oh, I didn't say this, but this is plus minus. Yeah, I think we had plus minus here. Of course, if you know what here, you can determine this sign precisely, but there are several cases, so I just wrote plus minus. So this plus minus sign is chosen so that this PB is a product. B is really a product. The same thing as here. Okay, so in this case, of course, the unique A prime looks like this, and by taking commutator with XX, you recover this. Okay, so in this case, you started from this, you extended this, and you got this. So we call this A prime the Shiraishi shift of A. Now, if you consider the basic relation star for B, then you note that A and A prime are the only products whose lengths are less than or equal to k that generate B. This fact means that the basic relation for B looks like this. Of course, I'm not saying that these are synchronized. These plus minus sign are of course determined, but in general I don't know, so I just wrote it this way. But this is already useful. So from this, you solve this, you find that we still don't know the plus minus sign, but anyway, you find that these signs are related by this. Okay, this is just a terminology. If when a product A does not satisfy 1 or 2 of lemma 2, in this case we have QA equals 0, we simply say that the Shiraishi shift SA does not exist for this A. So to summarize, we have this lemma here. Okay, lemma 3 says that if you take a product A with length k, and then if the Shiraishi shift SA does not exist, then QA is 0. And if Shiraishi shift exists, then QA and Q of SA, which is just QA prime, are related by this. So, okay. So we here considered one Shiraishi shift of this. But the basic idea of Naoto Shiraishi is to apply this Shiraishi shift many, many times. Okay, let's look at examples of multiple Shiraishi shifts. And let me start from a good one. This is actually one of the products in the standard form. And so this looks like x d d d d y. Okay, now you take commutator with xx and extend this like this, and then you ask what generates this. Well, this one. So this is but something I already said. With commutator with xx generates this one. So this is the Shiraishi shift of this. Then you think about Shiraishi shifting this. Once again, you extend it like this, and this generates this. So this is the second Shiraishi shift of this guy, but you notice that they have the same form. Okay, so the form changes, and actually the x and y at the end switches after one Shiraishi shift, and so it returns to the same form. So of course, it's just clear that you can repeat this forever. We use periodic boundary conditions, so these guys just move without changing forms in alternating manner. Okay, so in this case, you can Shiraishi shift forever. Okay, let's look at bad examples. For example, these two guys satisfies both conditions 1 and 2 of lemma 2. Okay, and they can be Shiraishi shifted, of course. And if you Shiraishi shift this, you get this. But you cannot Shiraishi shift this one. You can extend, but you cannot have anything here because this guy does not satisfy condition 2 of lemma 2. This condition first of all said that this should be either x or y, but in this case you have z, so you can never Shiraishi shift. This is much more trivial thing. Here you have identity. Okay, I didn't write anything, but you have identity. In this case, once Shiraishi shifted this, but you can never shift this, right? Okay, so and in these cases, you cannot Shiraishi shift SA. So you have QSA equals 0 from lemma 2, and then lemma 3 says that these are related, coefficients are related like this, but this is 0. You don't know plus minus, but anyway, this is 0, so 0 is 0. This shows that QA equals 0. Okay, so this guy can be Shiraisi shifted once, but cannot be twice Shiraisi shifted. This means that this has a coefficient 0. In order, and it is clear by repeating this, you find that in order for A to have non-zero coefficient, it must be Shiraisi shiftable forever, for many, many, many times. Okay. So let's look at the condition that you can Shiraisi shift a product many, many times. And for this, I think it's very useful to compare these two examples. Okay, both of them satisfy the condition of lemma 2. And the condition said that the left end should be either x or y. Okay, they satisfy. And in lemma 2, we didn't say much about this guy. But here you find that this next guy must be z. Because if this next guy was not z, then no, yeah, not z like this, and then you get z at the leftmost side in the next step. Okay, that's clear. So according to lemma 2, this could be either y or z, but this choice y was bad. It becomes bad in the next step. So this means that this one must be z. And of course, you see that this cannot be empty, but this is not important at all. This is very important. So in order to twice Shiraisi shift, you see that this guy must be z. And then you also note that all these products do not change by Shiraisi shift until its turn comes. Okay? So by repeating this consideration, you see that in order for a product to be many times Shiraisi shiftable, all these guys must be z. So we get this. Okay. Does this sound sloppy? But this is mathematically rigorous. And so we found from this that a necessary and sufficient condition that A can be shifted, Shiraisi shifted many, many times is just, first of all, the left end must be either x or y, and the right end must be either x or y. And in the middle, you must have all z's. Let me summarize this as lemma 4. Okay. Now I take any product with length k. This is the maximum length. And then we have shown that QA equals 0, the coefficient in this, the candidate of local conserved quantity must be 0 unless A is of one of these standard 4 forms. And here you have x, and here you just have z's. So this reminds you of this Jordan-Wigner business. But this is, of course, not a coincidence. The structure of XY model, this free fermion structure, is encoded in this discussion. Okay. So this A should be either one of these 4 forms. So the left end can be either x or y, and in the middle, you always have to have z's. Okay. So there are 4 patterns that we may call XX, XY, YX, YY for the trivial reason. Okay. And here is a remark about the solvable model. So we have not made use of the fact that H is non-zero. Okay. This means that all the results apply to the integrable model with vanishing magnetic field. Okay. And so this consideration applies to the local conserved quantities there. And for example, we have seen that this is a conserved quantity, but then you see that this is a sum of this XX type and YY type, right? And we have also seen that Q2 prime, that is like XY minus YX thing, is also a local conserved quantity. So in this case, this is a linear combination of this XY type and YX type. Okay, so that was a remark for solvable model. And now this is the end of step 1. Okay, so let's move on to step 2. So at the end of step 1, we have seen that you only have to consider one of these 4 standard forms. So let's concentrate on this YY type. Okay, and I can shift the coordinate and just concentrate on this one, right? Oh, I'm not assuming anything like translation invariance. I'm just changing the coordinate. And and our goal is to control the coefficient QC1 and to show that this is 0. Okay. But actually, we cannot simply treat C1. We also have to consider its Shiraisi shift Cj. Okay? And so Cj is defined like this by using j minus 1's Shiraisi shift like this. So this is 1's Shiraisi shift. For example, no, not that. So this is when j equal even, you have this form. When j equal 2, you start from x2 and you finally end at k plus 1 or something like that. Okay, and you notice that this one is of XX type. Okay, so now here we are dealing with YY type and XX type. Okay? And so this is XX type and this is YY type. These are Shiraisi shifts. And now we have many CJ, so we have to treat all these QCJ, but we don't have to worry. It's very easy, and we will see that all of them have the same coefficient. Why is this? Well, this is just a simple, and this is just the Shiraisi shift. So to look at the relation between this coefficient QCJ, first I assume that j is even, and consider this Shiraisi shift from Cj to Cj plus 1. The only thing you do is to start from this and add, take commutation relation with yy and get this relation, get 1. And you observe that also by taking commutation relation with xx, you recover this one. Okay. So this is the Shiraisi shift. And if you consider the basic relation for B, the only products with length k or less than k are Cj and Cj plus 1. And if you can also now compute the coefficient with sign, and here you take the commutator with yy, you get minus sign. Here you have xy, you get plus sign. And so this is the relation you get. So this shows that they are the same. Okay, and when j is odd, you can do basically the same thing with slight modification, and you also get this. So you will find that for all j, the coefficients are the same. So our goal will be to show that q equals 0. Now, we must use the magnetic field term like this. And we have to now consider something obtained by taking commutation relation with this x. So now let's define this new thing, dj, which is a product, which is obtained by taking commutation relation with x and this cj. Yeah, let's look at this. This is cj. Okay, it starts from x and just z, and you end at x. Oh, I'm assuming that j is even. Okay. Well, when j is even, then our Cj is xx type. So you start from x and just bunch of z's and it ends with x. And here in between you have site k minus 1. So you take commutator with x and you get y. So this is our dj. So this is almost like Cj. It starts from x and z, 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 but only at this one site you have y and z, 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 and x. Okay? And we ask, what are products with length less than or equal to k that generates dj? Okay, of course Cj generates dj with this guy. And as in previous business, we can also think about shorter products, which we denote by ej and ej plus 1, which generates dj in a familiar manner. For example, this ej looks like dj. It starts from x in the same side, and z, 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 and y at the same position, and z, 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 but it's slightly shorter and ends with y. Okay, and this is site k plus j minus 2. So if you take commutator with x, you recover this dj. And this is the same thing. It looks like dj on the right. It's the same thing here, y here, and z, 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 and but at this end you have y. And so if you take commutator with xx, you recover this. Okay, so these are shorter operators, k minus. Oh, so you notice that they are not. This is not in the standard form, but well, you never care because this is less than k minus 1. The length is k minus 1. This standard form lemma only applies to the products with length k. And so we are here. And of course, as for this dj, we know that q of dj is 0, but this is not useful at all. I mean, we are not looking at this. We are only looking at products that generates dj. Okay, so are these three the only products that generate dj with length less than or equal to k? Not at all. There are many, many, many products with length k that generates dj. Well, this is different from what we are doing for case B, in this case with product B. The product B has length k plus 1. And we only had to look at products that generates B and has length k or less than k. Okay? In that case, we only had to look at only these two products. But in this case, D has length k. Okay? So by using this magnetic field term, you can generate dj from many, many different products with the same length k. And of course, you can. There are some. There are some larger. There are some products with larger lengths that generates dj, but that's of course not necessary to consider. But as for this, from this length restriction on the length, we have to, in principle, take into account all these products A with length k that generates dj. But the lemma 4 saves us. Okay, there are products that generate dj with length k, but all of them except for cj is not in the standard form. Okay, that they are out of standard form. So this means that of course they enter in this basic relation, but the coefficient is non-zero. But these q's for these guys are all zero. So in effect, the basic relation for dj just consists of these three things. We only need to consider these three products: dj with length k, which is our main actor, and the shorter one, ej. Okay. So ej and ej plus 1 are defined here, I think, almost precisely, but let me just define it generally. So this short product ej has length k minus 1, and it's defined like this. Okay. So here you have something almost like cj, but this is slightly shorter. This has length k minus 1. Start with y and zk, and it's Shiraishi shift. Okay. And then I take the commutator and divide by this. Okay. So if you look at this part, then this is the previous page. It's exactly the same as this. And here you have cj, but here to define ej you have this, and here you have something like cj but something slightly shorter. Okay, so this is a general thing. And actually on and let me go back to the previous page again. Actually, I will discuss this carefully, but j is defined for dj is defined for j from 1 to k minus 2. But ej is defined for j from 2 to k minus 2. So here's an example for the case with k equal 5. So now, okay, so this is C1, y, z, 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 y, and k minus 1 is 4. So on this side, we use this magnetic field term, and you get this one. C1 looks like this, okay? And then this is C2, and so this is Shiraishi shifted, and here at site 4, we use the commutator with magnetic field term. So D2 looks like this. And now E2 is this thing, slightly shorter. And this is C3, D3, and E3. Okay. Now, did I say this? Here, probably I said this. So here I treated the case with even j. Okay, and the discussion depends slightly on the parity of j. So we need to consider the case with odd j separately. Okay, and in this case, cj becomes the original yy form yzzzy, and dj becomes like yzz. And here you have extra y. And here, in this case, actually the two ends, 1 and k minus 2, these are both odd. So we have to exclude these cases. So they are exceptions, and we will consider this in the next page. But anyway, in this general odd j case, Actually, here in this case, you don't see this general one, so you have to have at least k equals 7. But anyway, in this case, this is C, and this generates D, and then these are two E's that generates D. And of course, there are a bunch of other products that with length k that generates dj, but you don't have to think about this. You don't have to consider them because of lemma 4. So the basic relation for dj looks like this. Okay. Now we look at these two exceptional cases, j equal 1 and j equal k minus 2. Okay. And in this case, this is j equal 1. Okay. This is useful to look at, and this will show you why we have chosen the site k minus 1. So in this case, we had this y, and we applied the magnetic field term here at k minus 1, because you cannot apply it here. Okay? So we applied it here to get this. Okay? And now this is generated again by this E2 by taking commutator with yy and getting this. Now, why don't we have E1 here that generates this by extending it in this direction? Well, I think this is clear. I discussed this rather carefully. If you have something and if you extend it and you get something, you can never have yy, okay, after taking commutator. So that you have yy means that there's nothing which generates this D1 by adding something to the right. Okay. So this is exception, but this is a very nice exception. So this gives you a sort of terminating condition. Okay. So this is the basic relation for D1. Very similarly for k minus 2. In this case, this is generated by k minus 2, which looks like this, by adding yy here, but this is not generated by anything else. Okay, so you get this terminating condition relation here. Okay, now I think we are basically done. So we have obtained a basic relation for dj, and we have a bunch of j's, but a good news is that qcj are same. Okay, and well, this is an annoying new thing, and we don't know anything about this short product, so let's just call this weight coefficient q tilde j. And then we write down these basic relations for dj, but this looks nice. So these are two terminating conditions, and these are general condition for even j and odd j. And look, so this is a condition for j equal 1. What is the condition for j equal 2? Okay, j equal 2, it's even, so it's here, so it's minus q2 minus q tilde 3. And then here you have plus q2 and minus q tilde 2. So if you add them, this cancel out. And if you consider j3, you see that you have plus q tilde 3. Here you had here minus q tilde 3. And so they just cancel out. And if you can easily find out that if you just sum them up, you will get this relation. So there are k minus 2 relation, you get k minus 2, and you only get this term, this part, and all these things, because they are annoying unknown thing, but all these things cancel out, and what you get is k minus 2 times h times q equals 0. And k is of course greater than or equal to 3, so this is non-zero. And of course it's important, we have to use the fact that the magnetic field is non-zero. So this is non-zero, and so we can solve this relation to get q equals 0. So this means that qcj equals 0 for all j, and this is what we wanted. Okay, so as for the standard forms standard forms like yy or xx with odd k, we are done. We have shown that coefficients are 0. So there are some remaining tasks. So we also, for the same odd k, we also have to treat x, y, and yx. Okay? And then we also have to treat these guys with even k. So, actually there are 4 different patterns. So this for odd k, we are done. This for odd even k, this one for odd k, and this one for even k. But I think you believe me that they are not too difficult, and you can basically do the same thing. And actually there is some slight complication here for even k. this with even k and this with odd k. In this case, you have to treat dj and ej running from 1 to k minus 1. And k minus 1 should have a slightly exceptional form. But anyway, there's no essential difficulty. So we can show this for everything. And then this finally shows that qa equals 0 for all k with length k. And this completes the proof of the absence of non-trivial local conserved quantities. Whew. So I'm tired and hungry. So we have proved, actually there are 4 cases to do, and we treated the first case very carefully, and you can do the same thing for the rest of the 3 cases. And then we have the proof that this spin 1/2 xy or xx model with this Hamiltonian and non-zero magnetic field has no non-trivial local conserved quantities with length k, where k is in this range. This was proved by Yamaguchi, Chiba, Shiraishi in 2024 based on Naoto Shiraishi's pioneering work in 2019. Okay, and so here is a remark about non-integrability. So this is a empirical fact that all non-integrable models have series of local conserved quantities. Okay, we have seen this for the solvable XX model, and in that case, the free fermion expression told you that there are many conserved quantities. But for other cases like solved by much more difficult beta ansatz, they also find a bunch of local conserved quantities. So it seems to be a rule that whenever you can exactly solve a model, you also get a bunch of conserved quantities. So this means that it is strongly suggested this model is non-integrable. Okay, but I stress that this depends on the definition of non-integrability, right? And there is no clear definition of non-integrability. You know, if you can solve it, and then you say, oh, I could solve it, then it's integrable. Okay, so if you cannot solve it, we don't know what it means. Probably somebody much cleverer than us can solve it. So and this really depends on definition. And some people define non-integrability by the absence of local conserved quantity. So in this case, well, yeah, this theorem proves that this model is non-integrable. But you know, this kind of terminology question is not very fruitful. So the more important is what we can learn. And anyway, we learn this fact that this model has no local conserved quantities, or if you work slightly harder, you find that the only local conserved quantity of this model is the Hamiltonian itself. And this is a very strong information, and I believe that it has some implication on, say, time evolution of the system. Well, this should be explored more. So, but anyway, this theorem is a very strong information. And by now, there have been many extensions of Shiraishi's proof of absence of non-trivial local conserved quantities to various quantum spin systems. And for example, there are extensions to higher dimensional hypercubic lattice, the d-dimensional hypercubic lattice in dimensions 2 or higher. And then for spin 1/2 models, it has been observed that except for the classical Ising model, everything does not possess non-trivial local conserved quantities. So it means that almost everything except for the classical Ising model is non-solvable in higher dimension on the hypercubic lattice. Okay, and anyway, by looking at all these extensions, it seems that there is a very interesting and non-trivial dichotomy, that which is a simple quantum spin system is either integrable and known to be integrable and found to be integral by somebody clever, or does not possess non-trivial local conserved quantities, and it can be demonstrated by Shiraishi's method. Okay, so we are still not sure about this dichotomy, but it seems to be the case, and so there seems to be something much deep here. So there must be some deep relation between integrability and the absence of non-trivial local conserved quantities. And I'm sure that we will learn more in the near future So look, so everything started back in 2019. So this is still in the study is still in the early stage. So I think more will come in the very near future. Okay, so this is the end of this mini lecture in which mini course, the end of mini course where I treated this spin 1/2 XY quantum spin chain or XX quantum spin chain. And when there is no magnetic field, and I discussed that you can solve this model by using free fermion techniques to obtain exact energy eigenstate and energy eigenvalues. This was done by Leib, Schultz, and Mattis back in 1961. And in the second part, I discussed that this model with magnetic field is very likely to be non-integrable. More precisely, there exists no non-trivial local conserved quantities in this model. And it is likely that you can never solve this model. And this goes back to this other recent works. Okay, so that's the end of this mini course. I hope you enjoyed it. Thank you very much for watching. Goodbye.